Hi, in this video, we'll talk about 3 examples related to linear transformation. In our last video, actually, we talked about linear transformation and we did a few examples. And here we're going to see 3 more examples. So the first one, find the coordinates of the image of the point P23 under rotation of 135 degrees about the origin. So if you remember, actually, we obtained this rotation transformation, and if we rotate a point, let's say xy, and we have this matrix. Here we have cosine of theta, sine of theta, minus sine of theta, and the cosine of theta. So that is our, what is it? Standard matrix of this transformation. But here, just we need to substitute this value. Here we are given a 0.23, and we are just rotating this 135 degrees about the origin. So here we will have the image of this transformation. Let's say here we have 2, 3 will be cosine of 135 degrees, and the sine of 135 degrees minus sine of 135 degrees and the cosine of 135 degrees. And here we are given this point, that is 2 and 3. Then what will be the image of this point under this transformation? Just we need to multiply this and the matrix by this vector 2, 3. So let's just simplify, since actually 135 is a special angle. So 135 is sine 45. Also, this one is cosine 35. Okay, so here in the second quadrant, it is minus. So here we have minus 1 over square root of 2. And here we have 1 over square root of 2. And here we have minus 1 over square root of 2. Cosine also it is minus 1 over square root of 2. So here we have this vector 2 and 3. So now if you just multiply this, what do we have here? Here we have 2 equals 2 times this plus 3 times this. So that's just 5. So here we have minus 5 over square root of 2. And how about here? Here we have 2 minus 3. So here we have only 1. That is minus 1 over square root of 2. So that means that here, if you're given this point, let's say this vector, actually here P, whose coordinates are 2 and 3, if we just rotate this 135 degrees, anti-clockwise direction, this one is 135. So coordinates of this point as image, let's say it's P prime, will be minus 5 over square root of 2 and minus 1 over square root of 2. Okay. See another example. Let's choose purple. Okay, show that the transformation from R2 to R2 that projects a point onto the x-axis is a linear transformation, and find its standard matrix. So we have to answer 2 questions here. First, we have to show that it is a linear transformation, and number 2, we need to show that it is standard matrix. Actually, to show that it's linear transformation in 2 different ways, we can show this. If I just show that it is matrix transformation, it is done. It is a linear transformation. Or directly using the definition of a linear transformation, also we can prove that. So here we are talking about a point. Let's say this one is x-axis, this one is y-axis, because it's in 2-dimensional space. If you just pick any point here, let's say this P, whose coordinates are x and y. And what is the projection of this point on to x-axis? The projection of this point onto the x-axis is this point. Let's say it is P prime. So the projection is just dropping this from this label to the ground. So it will be x and y coordinate will be 0. So now I don't know if it's linear or not. So this transformation was going on here. Here, this transformation actually transforming this point, that's xy, into this point. It is x0. Right? So now I can just write it as a, what is it? Product of a matrix and the given vector here, or the point. So you see here we have x0. So here we will have, since it's from R2 to R2, here we will have 2 by 2 matrix, and here is our point, x and y. So to get x here, this should be 1 and this should be 0. And to get 0 here, this should be 0, this should be 0. So if this vector is u, let's say this vector is u, now what's going on here? So this one is equal to a times u, where a is this matrix. Okay, since this transformation is matrix transformation, then we know that it is a linear transformation. And what is it? Is standard matrix. Standard matrix is this 1 0 0 0. Actually, this matrix transforms a point or reflects a point onto the x-axis. That's it. Another example, let L be a line passes through the origin in R2. Okay, show that the transformation from R2 to R2 that projects a point onto the line L is a linear transformation, and find its standard matrix. Okay, actually it is a kind of projection, projecting a vector onto another vector. So we are talking about a line that passes through the origin. Let's say we are talking about this line. It is passing through the origin, and all right, show the transformation projects a point. Okay, we are given any point here. Let's say it is P, whose coordinates are x and y, right? And projection means that if you just assume that this is a terminal point of a vector, as if you are just projecting this onto this line, right? Because this should be 90 degrees. And what is this? Actually, we know that actually this vector, also, if I just consider this as a vector, it's just the projection of this point, vector onto this. So now, if I say, let's say this OP vector is, let's say this vector V. And this projection here, let's say it is W. Okay. And we know that actually, since we are talking about a line, it is passing through the origin, right? And also we need one more piece of information actually about this line. What is it? Also, we need to know its direction. So assume that this D is the direction vector of that line, whose coordinates are, components are D1 and D2. Number one, actually, first we had to show that it is a linear transformation. Actually, this operation is linear transformation. That is the first part of our question. And as you see here, it's just a projection. That means that we need to show that this projection of line, actually, what is it? Actually, here we have this x and y, right? Or simply, I can just write here PL of this vector is V, right? It's a projection, so onto D direction vector, that is V dot D over D dot D, and these are vectors, and this is just a scalar, and here we have vector D, right? And this is how we evaluate actual projection of one vector onto another vector. That is what we learned from chapter 1. So I had to show that it is linear transformation. Here, let's just prove this by using a definition. And as you know, in the definition, we have two properties. We have to show that actually both properties hold for this. Okay, first one is if you just pick two vectors, if you just pick any two vectors from there, let's say this U and V. And so now I assume that actually we understand these are vectors, because every time putting bar, It is not so practical here. So that here I have to show that this PL of U plus V is equal to PL of U plus PL of V. How do you show that? Again, if you just substitute there, what is PL of U plus V? And here instead of V now here, we're just projecting U plus V. So here we have U plus V dot D over, and here we have D dot D, and here we have vector D. So using the properties of dot product, I can just actually distribute this over U and this over V. So here we will have U dot D plus V dot D over D dot D. And here we have D, vector D. Okay, actually, these are all vectors with me. Put this bar so that you don't get confused with scalar. Okay, so now it's just a fraction because U dot D is a scalar. V dot D dot product, it produces scalar, right? So just using the, what is it? The properties of fraction, A plus B over C, I can just write it as A over C plus B over C. So that is equal to U dot D over D dot D. And these are all vectors. And here we have vector D. Plus, and the second one is V dot D over D dot D. And these are vectors. And here we have vector D. And what is this? It's exactly the same thing here, right? Just instead of V, we have U. That is the projection of U onto the line. And how about the second one? It's exactly the same thing. It's just the projection of V onto this line. So that is PL of V. So which means that the first property holds. That is the first property. And how about the second property? The second property is the first, if you just multiply by a scalar and transform, or first transform and multiply by the scalar, they must produce the same result. So that is PL, let's say our scalar is C, and multiply by V. So again, just substitute here, instead of V now, we have C times V. If you substitute here, we have C, V vector, dot D, over D dot D, and here we have vector D. So just since it's a scalar, I can just take this out here, C, because all of the things are scalar, right? So here we have V dot D over D dot D, and here we have vector D. And this part again is just exactly the PL of V. So here we have C times PL of V. So since both of those properties hold, that means that this transformation is a linear transformation. That means it's a matrix transformation. Now, in the second part, we are going to find the standard matrix. So what is a standard matrix now? Just actually, here I have to evaluate this and show that that is equal to, what is it? I should show that actually that thing is equal to matrix A times vector V. Vector V. Okay, I have to show this. So let me just continue here. That's PL of V. That is PL of, let's say, the components of V are X and Y. So by definition, what we have here? By definition, here we have the first vector, that is X, Y, dot, and here we have D, that is D1 and D2, over, and here we have D dot D, that is D1, D2, dot, D1, D2, and here we have vector D. Let's say this D1 and D2. Okay. So that's equal to, that is equal to, so the new denominator, let me just keep it here. Let me just keep it here. Here we have 1 over, what do we have here? Here we have d1 squared plus d2 squared. And how about here? The dot product of two vectors, x times d1. So here we have d1x plus, and here we have d2y. And here we have vector d, that is d1 and d2, equals, so still I just keep the denominator here, d1 squared plus d2 squared. So this is scalar, and we should multiply this by vector. That means that multiplying a vector by a scalar. So we should just multiply each component by the scalar. So here we will have this vector then. Here we have d1, d1x, d1, right? So here we have d1 squared x plus d1 times d2, d1, d2, and here we have y. And if you multiply this by the second component, here we have d1 times d2. So here we have d1, d2, x plus, and here we have d2 squared y. So now, actually, as you know, I'm just trying to show this, that's just the product of a matrix and the original vector. So how can I write this thing as a product of a matrix and that vector? From here, as you see here, x, y, it looks like a system of linear equations. So I can just write it as 1 over d1 squared plus d2 squared. And here we have a matrix. And here we have that vector, that x and y, x and y. So what do we have here? Here we have d1 squared, d1, d2, and here we have d1, d2, and here we have d2 squared. If we just multiply this matrix by this, x times this plus y times this, it gives us the first component. And multiply by the second component, d1, d2, x plus d2 squared y, it gives us the second component. So let's see here, what do we see here? It's just a matrix. If I just denote this by A, let's say that thing equals A, and what is this? It's our original vector, that is V. Here we have matrix A times matrix V. Let me just not do this dot. Okay, it's not dot product, it's just matrix product. So that means that it's a matrix transformation. We have already proved that it's a linear transformation, and that is, it is standard matrix is this. So here we have d1 squared over d1 squared plus d2 squared, and here we have d1 d2 over d1 squared plus d2 squared, and here we have d1 d2 over d1 squared plus d2 squared, and here we have d2 squared over d1 squared plus d2 squared. Okay. All right, that's it. Thank you very much.